Hello there, friend. Let's make a program that simulates a bit of a board game. And the way this board game works is that this board, which is just a list, we'll call this list yard. This list contains a fox and it contains a hare. After the hare jumps left or right, the fox always moves toward the hare, and that's how we complete a turn of this board game. The game ends if the hare jumps onto the fox or the fox moves onto the hare, because that would mean that the fox ate the hare. So certainly the board game would end. And in our board, which again we'll represent using a list, we'll have the F character represent the fox. These blank tokens represent empty spaces, and this H will represent the hare. So from there, let's think about how we want to create this board game. I want to make this board game recursively because there are multiple decisions that the hare can make each turn. The hare can either jump left or the hare can jump right. So let's begin with a recursive call to a function. We'll do a recursive call to yard because that's the starting state of our board, right? Yard up here is the starting state. From there, let's define the function and define the variable we're sending in. We're sending in the current state of yard. From there, let's just print the yard just to see what the current state is. And then let's consider the following. Remember, when we deal with a recursive function, the first thing we do in the recursive function is define a base case. Essentially, what causes the game to end? Well, the game ends if we can look through the yard and we can't see a fox or we can't see a hare, because that would mean either the fox ate the hare or the hare jumped onto the fox and therefore got eaten. So let's create a variable called flag. What we're going to do is we're going to loop through the length of the yard and just check if every element can, if some element has the hare character. If it does, we'll increment flag by 1 and break. At this point, x represents the index of the hare, which is good because now we know where the hare currently is in our current state of the board. Next, we'll do the same with the fox. We'll loop through the length of the yard and check if the fox is located at some index. If it is, we'll increment flag by 1 and break. Now y represents the index of the fox. So if the fox and hare are both currently on the board, then flag would get updated to 2. So if flag is less than 2, we want to return base case hit. Essentially, fox has eaten hare. All right. So we've set up the base case of our recursive function, essentially how the game is able to end. But if it doesn't end, then something needs to happen. Let's make it so that the fox always moves first. To do that, we set the current position of the fox to blank, right? Remember, y represents the index of the fox, so let's make it so that the fox is no longer where the fox currently is. The fox is either to the left or to the right. And how do we define where the fox should go? Should it go left or right? Well, we define the fox going always in the direction of the hare. So if the location of the hare is greater than the location of the fox, then we update the yard 1 index to the right with the fox symbol. Otherwise, the hare is to the left of the fox, in which case we move the fox one to the left. Okay, so now the fox is able to move using this little block of code here. The fox is either able to move to the left or to the right every turn. Okay. For now, let's just keep it simple. I'm going to make a new yard variable, which is a copy of the current yard. And instead of updating the original yard list, I'm going to update the yard new list. This way, I'm going to have many different copies of yard, so I can keep track in memory of, the states of the board. It's a little confusing, but basically, we complete our recursive function with a recursive call. We're just going to send the new yard variable over into the next recursive call. And that should complete the very basic recursive game so far, where the hare does not yet move. If we run this program, we see all of the states of the board. We see the initial state where the fox and the hare are in their initial positions. We see a recursive call where the new yard array has the fox move one to the right, then another recursive call where the next copy of yard moves one to the right, the fox moves one to the right, the fox moves onto the hare, the base case is hit, and the game ends. So far we have the fox moving, but we don't have the hare moving. So to do that, we're going to need to make sure the hare can make decisions. So this simple version here, where we're just making one copy of yard, isn't going to cut it. We need to make two copies of yard. One that represents the hare moving to the left, and one copy of yard that represents the hare moving to the right. So we'll make two copies of the current state of yard, and we'll update each of them accordingly. So we'll move the hare in a similar vein to the way we did the fox, right? So we want to make sure that the hare can't jump out of range, right? So if the current state of the board looks like this, like that, we can't have it so that the hare jumps to the left. Otherwise, we'd go out of index. So if the hare jumps left here, we are out of index. So then it would crash. So to prevent that, we only want to move the hare to the left if the position of hare, a -2, stays within range of the index of the list. So we want to make sure that if we were to move the hare to the left too, it's not going to go negative, as a negative index would crash the program. Okay, so then let's update the left yard rather than the right yard. We'll make it so yard left, the current position of hare is blank. We'll make it so that the index to the left of the current position of hare gets the new position of hare. Then we perform a recursive call. So that's one recursive call. That means that the hare can make one decision going to the left. But the hare can make two decisions. The hare can jump to the left, as we've done here, where we are recurring to the left, but the hare can also go to the right. So hare can also make a decision to go right. Let's check to make sure the hare doesn't jump out of range. So as long as the position 2 to the right of the hare is less than the length of the yard, to make sure we don't go out of range, then we can make it so that the hare can jump to the right. So yard right, current position of hare becomes empty character, and the spot 2 to the right of the current position of hare, new position of hare. we recur, right? So here's what the decision tree diagram of the fox and hare game looks like. We see here at the top, this is the starting state. This is the state of the yard when we first input yard into the recursive function. From there, the fox moves one to the right because the hare is to the right of the fox. And then the hare can make one of two decisions. The hare can either jump to the left, in which case we take this leftmost branch, that's the decision that's happening, or the hare can jump to the right, in which case we take the rightmost decision and lead to the state going down and to the right. So there are two branches because there are two possible decisions the hare can make. Each branch corresponds to a different recursive function call within the recursive function. So if the hare jumps to the left, then we get this state. Hare jumps to the right, we get this state. So let's focus on this state here where initially the hare jumps to the left. Well, the fox always moves in the direction of the hare, but let's have the hare move. If the hare were to jump to the left, well, on the next state, the fox just goes over the hare and eats it. So then the hare loses. If the hare loses, then we call that the edge case, right? So in that case, we don't recursively call anymore. We return. So the way this works is that we begin at the initial starting state. We recur down and to the left. We're now at this state. We recur down and to the left. Oh, well, this is an edge case. The fox has eaten the hare. So what the computer does is it returns and goes back to the previous most state, at which point we can explore a different branch. Then we go to the right, assuming that the hare jumps to the right, avoiding the fox. From there are again two different possibilities. The hare can jump to the left onto the fox, at which point this state would return. So we don't really need to check that. Or the hare jumps to the right, at which point the fox moves to the right and the game can continue. So we see that a recursive function explores the decision diagram of your problem depth first. That is, it goes downwards into one possible decision tree branch until it reaches an end case, at which point it returns and tries something else if it reaches the dead end. So this is just the first few levels of depth of our decision tree diagram, but it's good to look at because we're going to see that these states are exactly what are going to be printed when we run the program. Before we run the program, I am going to move the print yard from before the return, the edge case, to after the return, if the edge case is hit. This way we won't be printing the dead ends. We'll just see how the hare is able to survive. Okay, so there we go. This is what happens when we run the program. This is pretty similar to what we saw in the decision tree diagram, but it's complete. And on top of that, it's not in order, of course, because we can't print a decision tree diagram easily. It just prints the states as they come. So this here is the first state, the initial state, when we print the yard. Then, from that initial state, this is the leftmost state where the hare jumps to the left. Of course, we saw in the decision tree diagram that if the hare were to jump from here to the left, the fox would eat it, so we're not printing that edge case state. Instead, the fox jumps to the right. So instead, from the initial state, what if the fox jumps to the right? Well, then we get this state here represented on row 3. Then from there, the hare can't jump to the right because it's at the rightmost position of the index. So the hare must jump to the left. And then the fox moves from the second column to the third column. And the game continues. the fox moves to the right, 1, but then the hare jumps over the fox, which of course leads to a dead end in the next state because the fox can move and eat the hare, and the game continues until all the states are exhausted. So the fact that the game ended tells us that the initial function call ended, which means the game does not go on forever. All the functions were returned. This game does not go on forever because hare can't win. The hare cannot win given this initial starting state and the rules where the hare can jump to the left or to the right. The hare can't win. That's why we see the program has ended. Let's go back into our code. It'll be a little easier to see the state of things if we also print the depth. So to do that, let's begin at depth 0 at the starting state. Then in the definition of the yard, let's have the n variable represent depth. Or even better, we'll just call it depth. And what we're going to do is, along with printing the yard, we're going to print depth. Okay. So then we'll see the depth of each state that is printed out. This will make it easier to follow and see kind of what's going on. Lastly, we have to update depth before we recursively call. So in the recursive call, we're going to do depth plus 1 and depth plus 1. So as it recurs, each recursion is going to have a local depth that is 1 higher than the previous recursive function. Here we go. So here we see this is the initial state. There's only one initial state, so depth is 0 there. Then the initial state can branch off to the left, where the hare jumps to the left at depth 1, or to the right, where the hare jumps to the right at depth 1. We can probably put together a decision tree diagram just looking at the depths and the states as is, but it looks like, based on this program, the hare cannot survive beyond 1, 2, 3 turns. By the 4th turn, the hare will have lost regardless, which is why we're not seeing depth 4 printed out with any kind of state, because all of the states at depth 4 are losing states for the hare. So the longest the hare can go, assuming the hare makes the best decisions possible, is a depth of 3. Let's go back into our program. And in our program, we're going to make it so that the hare has more mobility, right? So instead of the hare jumping 2 to the left, the hare is going to jump 3 to the left. Instead of jumping 2 to the right, we're going to say that the hare can jump 3 to the right. So we'll update those lines accordingly. And then we're going to make the state of the board larger. We're just going to add more empty tiles. And then we're going to see what happens. Well, we have an error. We see that maximum recursive depth has exceeded. So that tells us that the program basically doesn't end, because the hare just keeps moving and moving and the fox keeps going, that we reach such a high depth without closing the functions and reaching a base case that we run out of memory, or Python won't let us go beyond the recursive depth limit. So to fix that, let's add another base case. Also say up here, if depth exceeds, let's say, 20, turn. Let's make a smaller state of the board so it fits on the screen. There we go. Interesting. So here's the state of the game. All of the decisions and states possible for the decision tree diagram if depth is not allowed to exceed 20. We see that we get a lot of these situations, these patterns, where the hare keeps jumping over the fox. So that hare jumps to the left, the fox moves to the left. The hare jumps to the right over the fox moves to the right. And basically, the fox can never reach the hare because the hare keeps outmaneuvering the fox. Until, of course, depth reaches 20, at which point it goes and checks a different decision branch. So we get a lot of these patterns, which tells us that basically the hare, it is entirely possible with this initial starting state that the hare never loses. The hare is able to essentially beat the fox because we never hit a return. We never hit the edge case. We have a pattern that goes on forever. So that's interesting. And here's all the other states. Here we also see the hare jumping over the fox pretty much forever. So it's safe to say that there's a lot of ways that the hare can win. Let's slow things down. I'm going to import time. I'm going to make sure depth doesn't exceed 10 so that the program can actually end. And we can see more decision branches. I'm also going to add a time sleep of half a second before we recur to the two branches. And that's, there's the starting state. And here's the hare moving around until depth reaches 10, at which point it goes and explores a different decision branch. We could definitely put together a decision tree diagram just looking at these depths, looking at the states, comparing it to the previous states, but it would take a little bit of work. We have figured out basically that the hare can win so long as the hare is able to jump to the left 3 and to the right 3, and that's what matters.